I'm excited to introduce our next speaker. He's pursuing efficient systems thanks to the benefits of economies of scale. And he's the founder of the Institute Arnas and a Shuttleworth Foundation alumnus. Luka develops long-range sensor networks that are used in conservation. And he's going to talk today about installations he's done of tracking green sea turtles, monitoring in Africa, and also monitoring forests in Peru. Please welcome to the Hackaday Belgrade stage, Luka Mustafa.
Hello everyone. I hope you had a nice breakfast and enjoyed the previous presentation, which is really awesome. So my name is Luka Mustafa and I like building things. So today's talk is about a number of things I've been building with my team at Institute Arnas in Slovenia, where we build future-proof hardware and a lot of very cool different systems. That might range from wireless optical communications, the system Kuruza, which you can see at the back of the demo table. So this essentially is wireless fiber, building to building. We work on IoT systems, have some modules for power scheduling, which is the core of a lot of the tech I'll be introducing today. And on our other branch, we do 3D bioprinting of scaffolds. So you've had a very nice introduction in the previous talk on what the scaffolds are and how they can be used. Our particular interest is being the technology partner in creating hydrogel structures, or for example, printing structures which have already printed vessels in them, so you can then directly introduce cells to very effectively grow tissue in 3 dimensions. And from that perspective, we work with research organizations and companies to deliver the 3D printing to their environment. And one of our other efforts is building open source medical devices as well, as part of the Project Guerrilla effort. But today I'll be talking about animals, and especially animals as sensors. This might sound a bit odd at the beginning, but from a very engineering perspective, what we can observe and measure we can use as a sensor, more or less. So our effort here is to firstly conserve the nature and see what's going on effectively. By, for example, understanding how penguin migrations in Antarctica and the Arctic happen, you can know what the effects of the global warming are, for example. By observing, say, angel sharks over there, which are very endangered, we can see the effects of coastal regions in, say, Africa and Canary Islands by various different environmental effects. And the video you've seen in the beginning of the green sea turtles of a very endangered species is that if we can fully understand how they move around, how they live in an environment, we can see their interaction with trash, which is very important, with all the plastics. With that, we can identify the sources of pollution in local areas. From that, say, policies can be formed that regulate the shipping routes, the ports, and similar things like this. And also something very interesting is, by understanding how the sea turtle ecosystem works, we can discover the yet unknown coral reefs so they can be properly preserved. So something we've been working on for the past year is a bunch of different solutions deployed in super remote areas of the world. So for example, we built a system for penguin monitoring in Antarctica, for monitoring water levels in Madagascar, for freshwater species conservation, an arboreal system in Peru to monitor the tropical forest, the sea turtle tags, and all of these solutions are backed with the LoRa long-range sensor networking, for various different applications that I'll introduce today. So firstly, we'll look at a few solutions a bit more in detail so you get a brief idea how the tech is built and what's inside the black box, essentially. So the turtle tags you can see here in the image are essentially small camera devices which you can attach to a sea turtle by means of an epoxy glue. To minimize the effect on the animal, actually a small base plate is glued to the animal and then the whole larger tag is attached with 2 screws such that that can be very easily replaced. But also the base plate as such can be cleanly removed from the turtle shell after a few weeks, meaning that there's absolutely no effect on the animal as such. Inside the unit, because the whole idea is that it's very much universal and can be adapted and a lot of different things can be done for different projects with it, it's one of the first sea turtle tags which can be fully disassembled. Inside is actually a Raspberry Pi Zero with a camera, a battery cell, a wireless charging module, so you don't need to disassemble the whole thing when you want to charge it, as the enclosure is designed such as to withstand the pressure of 500-meter depths underwater, so it will seal in any condition, essentially. So with these tags, we also have a LoRa module inside. And how this whole thing works, actually, is you will have a sea turtle with a tag on it. Once it swims to the beach, firstly, we can attach this camera tag to it. And in about 2 weeks, it will come back to form another nest. And exactly over that 2-week period, until it comes back to make the second nest, we can capture some very nice videos and understand a lot more about the animals as such. And why do we need IoT communications, essentially, is because once the turtle comes back to the beach, we need to know that it's there so we can collect the tag and remove it from the animal as such. And also there's about 100 gigabytes of video collected on every of these tags, so it's not entirely possible to download that wirelessly in any practical way. So we just need to get the information. Hey, our turtle is back, go find it. If we know the location, then even better. We remove it and then retrieve all the cool videos that you've seen. So we've looked at the internals already. If you are furthermore interested in this whole thing is open source and available online. And we've built it in collaboration with Soribada Initiative using a bunch of different cool technologies by a range of partners. And in a similar fashion, we've been tasked to figure out a system that can be deployed in a remote tropical forest in Peru to monitor animals climbing up trees and actually jumping from one to the other. For example, monkeys, leopards, or pretty much other large mammals. And the issue is we are in a forest in the middle of nowhere, hundreds of kilometers of nothing around, essentially. So how do we build a system where we can't just deploy simple cameras, come back a year later and get some images, but you want to get real-time data of how movement happens and also get real-time images. So we've designed something which will capture an image on actually motion, just PR detection, quite simple, with additional Wi-Fi networking built into the system and solar charging. So you put it up a tree, and then you have a local wireless network at the canopy level. From there, it's uplinked to a satellite connection and sent back to the internet. And the LoRa communications come into play that we can monitor all the devices and essentially say, hey, turn on Wi-Fi now, and you can turn all the equipment on to conserve a lot of power, because we all know that Wi-Fi routers and pretty much every high bandwidth communication means will consume a lot of power. So the whole trick is, how do we make this sufficiently low power while being super robust for remote areas? Another solution of this sort is a problem that occurs in Madagascar, where there's a few species of very endangered fish. And literally this goes for like 10 or 50 specimens of the last specimens of one type of fish there, which best grows in one of the rivers. but the drought can have a catastrophic effect on that species, as it will die out if it runs out of water, essentially. So the system we built encompasses essentially a camera to capture the environmental effects in the local area, can do also some edge computing, so process the image to form an answer, as well as it does the ultrasonic measurement on water depth. So you suspend the whole device across a river, like this, for example, and via LoRa you can then send results to a local base station if there's one, or through a satellite modem, with the purpose of actually someone going out there with a bucket, picking up the fish, putting them in a pond for the 1 month of, say, water running out, and once the water is back in the river, they return the fish, and hopefully they'll happily live forever after. But this is actually the effort required for quite a lot of very endangered species to survive in this environment at the moment. And lastly, one of the interesting systems is the camera I have here, and you can have a look at the back at the demo table as well later on, is a PMP system for Antarctica, where these cameras are placed essentially on the various beaches where penguin colonies will be for a few months. And we want to take regular images to count the number of the population, to observe the migrations. And the challenge here is this is obviously in Antarctica, so it's very far from everything, and there's no good means of sending very large images. So obviously the basic function that we built is take an image, store it to the SD card or USB drive inside, come back in a year with a boat, retrieve the memory, and get the photos. But that's a year. And in a year, a lot of things can happen. If we want to be able to positively react to our environment, we need answers much sooner than that. So with low power, long range communications, we can add edge computing to these devices, meaning that you take a photo and you guesstimate essentially there is more than 100 penguins there, or there's just one, or there's none, or something along the lines. This is already a very useful answer, which you can then, in a very few bits, send at low power quite far away. And inside these cameras, which are very similar to the ones I've shown previously for the Madagascar, is again Pi 0 with a camera for power scheduling, plus some modems for either satellite communication or LoRa long range. So over the past year, we've been looking at a bunch of these solutions and found a number of key challenges. And these are very important ones because they're not necessarily technological, but need to be solved in order to successfully deploy solutions all around the globe. Firstly, everything needs to be simple and essentially low cost, suitable for untrained use. And that, for a lot of hacker DIY projects, it's quite a challenge. So our approach is try to build things that are zero config, that will do the basic functionality instantly, but you can add then different settings and tweak with it if you so desire. And lately, one of the best methods is just have a Bluetooth low energy interface and a simple phone app where people can type things in. Also, real-time information on sensors or other devices you deploy is very much appreciated. So that doesn't necessarily mean you need to shift all the data from the device you have in an area somewhere. But for example, if in a jungle you have a camera sensor, what you really want to know is it still working? Like, how many photos did it take in the last day? Because that gives you the confidence that you will get a result 6 months after, once you go and retrieve a number of gigabytes of that data. And if you see it's not working, you can always send someone out there to just replace it and really not miss out on any opportunities there. And for the underlying technology of long-range IoT sensor networks, it's a really demanding area where you need to know if you will have some communication coverage. And it's not simple to deploy your own infrastructure there. So having a network coverage map is very much essential. So we've decided to use the LoRa and LoraOne technology. So you might be familiar with this and the Things Network project, which is essentially a public LoraOne network deployed globally by an open community of individuals and companies, which allows you to do reasonably low-speed communications up to, say, 5 to 10 kilometers in more urban areas, or with a line of sight, it's easy to do even 50 or more kilometers. And just adding this to, say, a Raspberry Pi, we can have, say, a counter which will just, in the simplest instance, send the number of photos our camera has detected over 5 to 10 kilometers to the base station, along with the battery level, and then we can know our network of sensors, wherever we deploy it, it's working. So the typical infrastructure of LoraWAN networks is you have a gateway, which is essentially a device of this sorts, and there's very many different designs from, say, Raspberry Pi with a concentrator board. So this is the radio front end connected to the internet via 3G, 4G, Ethernet, Wi-Fi, you name it, to like very expensive solutions from different vendors. This is an open source design which we posted online recently and can check out. Is essentially a collection of a number of different open source projects put together in essentially a pipe for a waterproof deployment outside. And there's a bunch of these now deployed here in Novi Sad, around Slovenia, and I believe in the US as well. So the key technical unknowns in deploying a low-power IoT network are as, what is the coverage of my gateway? Once you deploy a gateway, you want to know what it does, essentially. Does it cover the immediate area of 100 meters when you put it up in the forest? Does it go as far as we need to deploy our sensors? What's the coverage on top of a tree? Like, these are all reasonably difficult questions to answer without trial and error. Now, if it's in a city, I can always take a device, drive around with a car, and see the coverage. And this is actually what the TTN Mapper project, which is an open source LoraWAN, the Things Network coverage mapper website does. You take a device, you drive around, and it will just log the signal at every position and show you a nice map. But in all the different deployment scenarios, this might not be as simple. So we've, for our own initial purpose, deployed first a drone configuration, which has a LoraWAN device on it, sending pings at regular intervals with the GPS position to the website and creating coverage maps. So taking any off-the-shelf drone, putting a small box with your custom electronics on it, you fly it in a specified pattern, and you can determine the coverage map. So here is a demo of a field in Slovenia where we fly around with a drone in a given path, and we can determine the coverage of a gateway. For a demo, the gateway is actually here in the middle, so all of this is very good coverage. But we can see essentially the signal level over an area of the field. Obviously, this you could do by just walking around in the same pattern. Now imagine this is actually on like tree level, 50-meter high trees in a jungle where it will take you months to walk around and a few hours to climb up every tree to find out which tree has sufficient coverage for your sensor. So actually having an automated system is very, very helpful in this perspective. And also something you can do easily is then check coverage at different levels above the ground. So this is the same field as we've seen earlier, but at different levels above the ground. So we can essentially know the coverage on top of a lamppost, for example, on the street level, how it changes in between the two, or across a large body of water, say a bay where we have our sea turtles. But taking this even a step further, because we can fly in 3D and get measurements, we can measure the real-world radiation patterns of our gateways. So this is not a typical diagram you would expect, from an anechoic chamber, essentially, where you test the antenna and do all the rotations. But this is actually the radiation pattern you get from an antenna on top of a building or on top of a tree, with all the imperfections from the ground plane effects to bad cables, bad connectors, whatever happens there, you actually see this in the real world. And then you can take this data, plug it into the radio mapping software, or radio modeling software, and use the real coverage or real radiation pattern of the gateway to determine the coverage map with much higher precision later on. And extracting this to something which is more similar to the diagrams we're used from normal antenna data sheets, you would see something like this. So obviously an omni antenna as you would expect, and you can see some side lobes between quarter wave omni antenna with DIY, you see quite some imperfection, or a collinear antenna where you can see all the side lobes essentially as expected from the design. But even more importantly, this can give us answer to which antenna is best for the application we're doing. So for LoraWAN 868 megahertz systems, you will see quite a lot of this short rubber ducky antennas, which are actually not omni antennas in a lot of cases, so that can create quite some problems compared with larger quarter wave ones, which will definitely have an omnidirectional pattern. So with the mapping, we've tested a few of low-cost antennas and found this results. Now, as we can see here, we have an omni antenna, standard 3 dB omni antenna, which you would expect. And from this, we can see that the gateway in the center, there's reasonably low coverage upwards from the gateway and a nice uniform pattern around the antenna. However, with a lot of the short antennas which are quasi-omni but are not actually, you will see that all the energy is actually radiated upwards and the coverage is much worse in the same area. So it means that you can quite often buy antennas which you will assume are omni, but they're actually pointing upwards, which is completely useless if your gateway is ground level 10 kilometers in one way. And this is exactly the example we can see here. So what I'm showing in this slide is blue area coverage of a gateway that is about 10 kilometers in this direction, and this missing piece here is actually the shadow of a forest. So when you deploy a network, if you do proper mapping out and properly test the coverage, you can know essentially which part of the field your devices will work, so you don't get to a case where you say, yeah, it should be right, the coverage is there, but then you end up with half of the sensors, for example, in a field situation like this, not having connectivity. And a few key learnings to conclude is when you do deployments in very remote areas, it's always very key to find methods to minimize time in the field. So instead of climbing up a tree, putting a gateway there and figuring out it doesn't work, you can just fly a drone up there, do tests in about 10 minutes, and then find the best tree to position your gateway, for example. You can do the same for a building. You fly it around, find the best spot, and build a mast there. And it's quite important to note here that a lot of this work, say climbing up, not as a hobbyist, but in a more professional world, will require a certified climber to come there that will cost a few €100 an hour to put something up, a tree or a building. And it's not necessarily good to figure out then, hey, we should kind of test this out before we pay someone to climb up, dismount equipment, and put it in a building next to ours. And we've done a lot of tests and mapping, for example, in the Principe Island, just off the west coast of Africa, where the sea turtle monitoring project is going on, where the tricky situation is we can reasonably well put the gateways up in the urban area with some internet and 3G connectivity to cover this area where the beach is, where we will conserve all the turtles, and we see that we will get reasonably poor coverage. So if we want to make sure that we get the ping from every turtle when it comes out of the sea to the beach, we need a good method to essentially map the coverage in this remote area effectively, move the gateway, and find the best solution. So I'll leave you with a few learnings from everything we've done. Base station height is usually the biggest problem for IoT networks, and especially if you're in like a tree area, you want to go as high as possible, and that means trying out a lot of things and seeing what works best. Health and safety is usually the biggest cost associated, not the equipment as such. So really doing time-effective deployments is the key. You might go to a jungle for a week. You need to deploy a network and a bunch of sensors. I invite you to check out our website. We're publishing all of these systems open source as we develop them, so you can hack them, you can build things on them, you can do anything you wish with them. And feel free to get in touch if you would like to work with us. Check out the booth at the back. And also, if anyone is looking for a job, we're looking for electrical engineers at the moment here in Novi Sad in Serbia and in Maribor in Slovenia. So feel free to chat to us. Thank you very much.